In this video, we're going to investigate different kinds of isomers. So in general, isomers are compounds that have the same general formula, but they're different molecules. And we have three different types of isomers. So this definition that I've got here right now, this is just sort of our general definition for all three. And then there's a little something extra that's going to set the three apart. So taking a look at the first kind here, we have something called structural isomers. And again, I've put isomers are compounds that have the same general formula but are different molecules. So how are they different in this case? Well, they're different because we are going to connect the carbons differently of the parent chain or the longest chain. And this is going to create different parent chain lengths. So let's take a look at an example here. So let's take a look at drawing C4H14. And I only want, in this scenario, 4 answers for the structural isomer, but just keep in mind that there are actually 9 answers. So the first answer I would draw would be simply to take this C7H14 and draw out everything as a straight chain. This is our low-lying fruit, if you will. And it gives us this molecule here. You can count it up. There are 7 carbons. And we're going to call that one heptane. Now there's another version we can draw of 7 straight carbons. You can bend the carbon up here, but it's still going to be a chain of 7 in a row. So no matter how you bend it, we've only got one heptane. So our next goal is going to be to take it one step down from heptane and look at what kind of hexanes can we draw. So I've drawn the first one here, hexane. 1, 2, 3, 4, 5, 6. So there are 6 carbons in a row. There's my hexane. And what I'm going to do is I am going to take a CH3. So in essence, we're kind of removing sort of this end part here, and we're trying to attach it to a different place on our chain. So you can clearly see that right here I've kind of left a space for that CH3 to go. And when we put in that CH3, we now no longer have a heptane. We've got our longest chain of 6. We've got a hexane, and now we have this group here, which is our methyl group on our second carbon. So it's going to make a 2-methyl hexane. So at this point, you should ask yourself, is there any other version of hexane I can make where I just move that methyl group around? And there does happen to be one. And you can see that little notch there in my picture. That's going to be our methyl group. So again, we have 6 in a row. And now this time we have this to be on the third carbon. Hence, we have a 3-methyl hexane. I don't think we can have a 4-methyl hexane because I think that would be exactly the same as 3-methyl hexane, but just flipped over. So then you start to ask yourself, okay, what about pentanes? How many 5-chain ones can I make? So you draw your 5, and then you say, again, I can't put in any methyl groups on the end. Let's start with the second carbon here. And so we can actually put one up and one down. And so again, we have our chain of 5, pentane, and we've got a couple methyls both on the second carbon. So 2, 2 dimethyl pentane. As well, too, for more answers, all we're going to do is start to move around these methyl groups. So the other answers to this question would be a 2,3, you're just moving one of the methyl groups over. A 2,4, you're moving it over again. A 3,3, they're both moved to the middle. And a 2-ethyl pentane. And a 3-ethyl pentane. So those would be all of your 9 different answers. And if you drew all of those, they would all have the general formula of C7H14. Now you're probably wondering what happens if okay, these are all pentanes. Are there any butanes? And I put a little note here that if you try to draw a chain of 4 and then try to put a group of 3 off that chain of 4, you're just going to simply recreate one of the previous 9 answers. You think it's got a different name like propylbutane or something like that, but it would just actually be one of the answers that we already have. If you don't believe me, draw it out and find your longest chain and go from there. Second type of isomer is called a positional isomers. So again, compounds with the same general formula. What makes positional isomers different is that we're going to locate the multi-bond, not band, multi-bond in a different spot on our parent chain. So we're going to find that this type of isomer can actually apply to both alkenes and alkynes, unlike our last one that was just dealing with alkanes, at least in that example. So let's name and draw all positional isomers of heptine. So heptine, that's 7 carbons. The Y tells us there is a triple bond in this molecule. So the first thing I'm going to do is draw my 7 carbons and put my multi-bond in the first bonding spot here. So not the first and second carbon, but our first bonding spot. And that's why we're going to call this one 1-heptine. To get a different answer, we're just going to take this multi-bond and move it over to the next place. We're going to have a 2-heptine. So that would be our first bonding spot. That's our second bonding spot. Again, not to be confused with first, second, and third carbons. And then our next answer is going to be 3-heptine. Again, you can see we've moved over one more spot. You're probably wondering, is there a 4-heptine? And the answer would be no. There would be no 4-heptine because it would be the exact same as 3-heptine. It would just be flipped over. But let's not forget, and I find students get excited when I ask this type of question, don't forget to draw the hydrogens in. I know I haven't drawn them in here, so there's some of them. Sorry I didn't take the time to put them all in, but make sure you add all the hydrogens in. On to our last type of isomer, which is called a geometric isomer. Another name would be a stereoisomer. And in fact, we're going to even know these by a different name once we get into this. So again, these are compounds where same formula, but are drawn differently. Now the difference for these ones is that we're going to actually draw this differently in 3 dimensions. And this is weird because on a piece of paper or even on this PowerPoint slide, things are in 2 dimensions. So there are some dotted lines and some little triangles to set these 2 situations apart. And we're going to take a look at how I do these molecules. So let's name and draw 2 different versions of 2-butene or butene. So what I like to do here to set these apart is I actually like to sort of start in the middle of the molecule. So I'm actually starting at this 2 part here. Now butene tells me that there are 4 carbons to a bit of a chain. So really what I've got here is my second and my third carbons that are listed. So what I'm going to do next is I am going to draw a couple of bonds and I'm going to draw in the rest of my chain. So you'll now notice that we have 1, 2, 3, 4 carbons. In terms of our bonding spot, that's our first, that's our second, and of course that's our third. But we're just interested in this 2 spot here. And I also do like to make sort of a big deal out of the hydrogens like that. Put those pointing down there. So if we had to name this one, oh actually you know what, we'll name it in a second here. Let's go on to the other version here. That's going to look pretty much remarkably similar. I'm going to start in the middle, we're going to build up. But what we're going to do here, kids, is we are going to switch that group and that group around. And when we do that, you'll notice we have a hydrogen up top and our methyl group below. It's not even our methyl group, it's just part of our main chain here. In terms of naming these 2, they're both 2-butene, but this first one we're going to call cis-2-butene, and the second one we are going to call trans-2-butene. Now, how can we tell those apart? Well, I got a good system for this. So the carbon chain itself looks a little like this shape here, which in essence is the shape of a U. But if you were to turn a U on its side, it would become a C, and that's the first letter of cis. Over on our other example, we have a sort of a straight line here of carbons this time, and if you just randomly cross the line for no reason and made it into a T, you would have your trans-2-butene. So that's how you can tell cis and trans apart. And by the way, it doesn't necessarily even need to loop up. It could also go down, or this one could go in this direction. Doesn't really matter, you can flip them around. So let's name and draw 2 geometric isomers of 3-octene. So again, when I go to do this one, I am going to build out. So the C part is always my starting point. Now, first thing I got to think here is that octene is 8, so I have to add 8 octenes to my structure. So what I'm going to do first is I'm going to work on maybe the left side here. I'm going to add 1 CH2 group here, or 1 carbon, and add the hydrogens afterwards, and another one here. Now, why have I done that? Because when I work backwards like this, that's the first bonding spot, that's the second bonding spot, and that's my third bonding spot. And that's what I want. I want a 3-octene. So now that I've got that ready, I just need to add the rest of my carbons in. I already have 4 in line here, which means I need another CH2. That's 5. There's 6. There's 7. And there's my 8th one. And then don't forget about your 2 hydrogens here. But sometimes I'm lazy. And you can write out these 4 carbons and 9 hydrogens, but sometimes I'll just write it like that. So those 2 molecules are the exact same thing. This is not a butyl group here. This is just the chain that I squashed down because I was too lazy. We also have, and we're going to call this one the cis, right? Because this is in our cis formation. So we also have our trans 3-octene. So in essence, this is again going to be the exact same molecule, but what we're going to do is we're going to flip-flop that H and that C4H9. They're going to look like that, and now we have our trans version of our octene. I should also make mention that these hydrogens here on either of these chains are places where we could add some methyl groups or something like that. So it is possible to have a substituent coming off these 2 chains. Got one more question here, which is name and draw 4 structural isomers of C5H10. Now this is different than our earlier question. I think the one I asked earlier was C7H14, which meant it was all single bonds. C5H12 would represent pentane. But what we've done is we have removed 2 hydrogens, meaning we've got at least something with a multibond, and maybe even something with a ring. So let's take a look at some of our answers here, and there are quite a few answers. In fact, there's 12 different answers for this question, and I think I've got 4 here on my slide. So the first ones would be a structural isomer, a pentene. We've got our first answer here is a 1-pentene, and we got our second answer here is a 2-pentene. Now what you can also do is you can also have some substituent groups come off these things. So here we have a 2-methyl-butyonine. So again, you find your longest chain. There's your bute part. You got your multibond in the one spot, wherever that happens to be. And then you've got this methyl group coming off over here. So there's your methyl part, and there's the 1-butene part. So you could move that methyl group around, or you can even move the multibond around to see if you can come up with some different versions of that. There's probably a 2-methyl-butadiene possible. You can also get some rings. So again, here we've got a cyclopentane, and if you count it up, there are 5 carbons and there are 12 hydrogens, so that is C5H10. And then there's actually a bunch of different rings you can make. For instance, you can make a cyclobutane that has a methyl group coming off it, and then a cyclopropane. There's a few different answers in that direction. So this is sort of a different type of question. I did say it was structural. In fact, maybe I could have just said, even left out the word structural and just put isomers down. And then it ends up being a question where we've got alkanes, alkenes, and alkynes, kind of everything rolled into one question.